Good days, viewers. I want to start some series of lessons in some important area in chemistry. Now, to start with today, I will be looking at an aspect which is actually referred to as energy relation in chemical reactions. In looking at energy relations, of course, we need to start by looking at what energy is. What is an energy? An energy is the ability to do work. This, of course, is what we've learned over the years. Since while we're even in primary schools, we've been learning about energy. And of course, we learned a lot also about the forms of energy. There are several forms of energy which include kinetic energy, potential energy, chemical energy, electrical energy, nuclear energy, light energy, solar energy, sound energy, heat energy. And as a matter of fact, here we will be focusing on that aspect that has to do with heat energy. But before then, we want to look at law that govern the energy, which is referred to as law of conservation of energy. And the law simply states that energy can neither be created nor destroyed, but can be converted from one form to another. Can neither be created nor destroyed, but can be converted from one form to another. And we will look at heat reactions, which in other words is referred to as enthalpy. Heat reaction. In other words, we call that enthalpy. When we talk about enthalpy, what is enthalpy? Enthalpy. Enthalpy. What do we mean by enthalpy? Enthalpy is defined as the heat content of a substance. The heat content of a substance. And we are talking about the heat content of a substance. The heat content of the substance could either be positive or negative. Could either be positive or negative, depending on whether heat is being given out or heat is being absorbed from the surroundings. And enthalpy is usually represented with a letter H. I mean capital letter H. That is how we represent enthalpy. And there are basically two types of enthalpy or heat reactions. These include exothermic reactions, and the second is endothermic reaction. Now, we pick them one after the other. We look at exothermic reaction. Exothermic reaction is a type of reaction in which heat is given out to the surroundings. Very often, students are often confusing the definition, but I wish to say at this point that exothermic reaction is a reaction in which heat is given out to the surroundings. Permit me to bring in a concept which we've been learning over the years, also in basic science or biology. Of course, we have learned about skeleton, and we learned about the types of skeleton, one of which is exoskeleton and endoskeleton. From what we know, exoskeleton is a skeleton outside the body. Exoskeleton outside the body. While endoskeleton is a skeleton inside the body. So we bring that picture to the concept we are looking at today. Exoskeleton. Then I'll be looking at exothermic reaction. Now, exothermic reaction, like I said, is a type of reaction in which heat is given out to the surroundings. And in this kind of reaction, the heat energy of the reactant is greater than the heat energy of the product. I said the heat energy of the reactant is greater than the heat energy of the product. That is exothermic reaction. Heat energy of the reactant is greater than heat energy of the product. And for every exothermic reaction, delta H is negative. Delta H, which is change in heat content, is always negative. Delta H is negative. That is for every exothermic reaction. Delta H is negative. That simply means that delta H, for it to be negative, HR must be greater than HPR. HR must be greater than HPR. That is the condition under which your delta H can be negative. And given the formula where delta H is equals delta H is equals to HPR minus HR minus HR, that will make our delta H to be negative. That will give us a negative delta H. That will give us a negative value for delta H. That is a exothermic reaction. And we have several examples of an exothermic reaction. And that will include, the example include addition of tetraozosulfate acid to water. Addition of tetraozosulfate acid to water. What do we mean by tetraozosulfate acid? It's an acid, of course. It's an acid. An addition of it is what gives us the addition of, like I said, addition of tetraozosulfate acid to water. You must understand at this point that there is a way we dilute acid. Acid are diluted on the basis of we dilute acid by adding acid to water. We don't add water to acid, but rather we add acid to water. And if you want to go the contrary way, you want to add water to acid, that could result into an explosion. So we have to add acid to water. And this, anytime we are doing that, you're adding an acid to water, that reaction is an exothermic reaction. I mean, it will generate it, it will produce it to the surroundings. Another example is dissolution of sodium hydroxide in water. The solution of sodium hydroxide in water. When you take sodium hydroxide, either the crystalline one or the granulated one, and then you dissolve in water, particularly for those of us that have been preparing liquids or whatever soap, you will realize that the moment you add it to water, the container will be very hot. That produces heat and is an example of exothermic reaction. Another example there is reaction between an acid and a base. Whenever an acid is reacting with a base, that reaction is an exothermic reaction. It will generate heat. Another example is the reaction between hydrochloric acid and magnesium ribbon. Reaction between hydrochloric acid and magnesium ribbon. And also we have the reaction between anhydrous copper 2 tetrasulfate 6 to water. Reaction between anhydrous copper 2 tetrasulfate 6 to water. All these are some examples of exothermic reaction. And exothermic reaction can be presented in an energy profile diagram. And of course, in energy profile diagram, in drawing, you first of all look at the condition for the reaction. And what is the condition for drawing? You have to understand which one is greater, and which one is smaller. You want to know that which of it is greater. Is it heat of reactants or is it heat of products that is greater? So depending on the one that is greater, that's what will guide you in the drawing. Now you have your vertical axis, which is a part where we have our energy. So energy is on the vertical axis. That's the energy profile. And then we have two marks made on it. Two marks are made on the vertical axis. And bearing in mind that the heat content of the reactant is greater than the heat content of the product. So our HR, we occupy the higher position, which is a greater position there, while our HPR, we occupy the lower position. And as you know that every reaction starts from the reactant. So this is the line of reactant, and the reaction starts from the reactant. And then from there, it goes up and comes down to the line of products. That is an example of an exothermic endothermic reaction. And on this horizontal axis, we have the reaction parts. We have the reaction parts, reaction pathway, and between this peak, the peak here, and the line of reactant, between the peak and the line of reactant is our activation energy, which is often represented with EA, capital letter E and small letter A. That's activation energy. And when you trace the line of product to your HPR, when you trace your line of product to the HPR, the difference between the HPR and the HR is your delta H. That's changing its contents. That's your delta H. And of course, you know that we have your reactant here, reactant R, and you have your product here, product on this side. Now, this peak is called activation complex. Activation complex. Activation complex. That is a typical example of an exothermic reaction being represented on an energy profile diagram. Now, we want to look at the second part, the second type of enthalpy reaction. And that second part is referred to as an endothermic reaction. Endothermic reaction. Endothermic reaction. What is an endothermic reaction? Like I talked about the skeleton that we're familiar with before, endoskeleton means skeleton inside the body. Skeleton inside the body. That is endoskeleton. And bringing that picture to this point, then you want to talk about endothermic reaction. An endothermic reaction is a reaction in which heat is absorbed from the surroundings. An exothermic reaction is a reaction in which heat is absorbed from the surroundings. And for endothermic reaction, the heat content of the product is greater than the heat content of the reactant. The heat content of the product is greater than the heat content of the reactant. That is for endothermic reaction. And of course, we know we have a general formula for enthalpy, which is delta H equals to HPR minus HR. For this kind of reaction, when you subtract your heat of reactant from heat of products, you are going to have your delta H giving you a positive value. Positive value implies that heat is taken in, is absorbed. Whatever you are taking is positive, is your own. Whatever you are giving out is no longer yours, it's negative. That is why exothermic reaction is negative, because heat is given out. You are giving out heat, is not yours. But now you are taking in heat. Whatever you are taking in is yours. That's positive. That is why endothermic reaction, delta H is positive. And if our delta H is positive, that is the only condition it is only when our heat of product is greater than heat of reactant, that's when our delta H can be positive. Now, there are several examples also to this effect of an endothermic reaction. Number one example is dissolving glucose in water. Dissolving glucose in water. This is an example of an endothermic reaction. You are dissolving glucose in water. When you do that, it will be an endothermic reaction. Now, how actually do we actually know? How do we know endothermic reaction? It's like you pour a cold water in a glass cup. When you pour cold water in a glass cup, you see the surrounding of the cup, how it will look misty. It will appear as if clouds surround the glass cup. and you begin to see some droplets of water coming down, dripping down from that cup. That's exactly what you see with an endothermic reaction. So endothermic reaction, you feel the reaction, it feels cold. It feels cold. That is how you identify an endothermic reaction. When you fill the container where the reaction is occurring, it will be very cold. And you see the outside looks as if you have something like cold water inside the container. That is how you identify an endothermic reaction. And like I have given example, I said glucose dissolving it in water is an example of an endothermic reaction. Also, dissolving ammonium chloride in water is another example. Dissolving potassium triosonate 5 in water is another example. Addition of water to sodium ethanoate is another example. Also, we have addition of water to ammonium triosonitrate 5 crystals. This one is another example of an endothermic reaction. Reaction between blue copper 2 tetrasulfate 6 crystal with sulfur 4 dichloride oxide. This is equally another example of an endothermic reaction. All of these, when you dissolve or you react to them, is going to give heat, or absorb heat into the system. And by that, you fill the container, it will feel cold in your hand. And like we did under exothermic reaction, we're going to represent this reaction also in an energy profile diagram. In an energy profile diagram, we have this diagram that we're having now. Energy profile diagram, we have the vertical axis, a vertical axis. We also have our horizontal axis. On the vertical axis, we're going to have two marks there. Knowing fully that in endothermic reaction, that the heat content of products is greater than the heat content of reactant. So here we have heat content of products. Heat of products. And below we have heat content of reactants, HR. And you know that every reaction starts from the reactant line. So this is the reactant line. So this is HR. HR. So the reaction starts from HR and terminates at the line of product. This is an endothermic reaction. And of course, you know, this is energy axis. This is reaction parts. Reaction parts. Now, when you trace this heat of product to the line of product, and then you also trace this one to the other end, trace to the other end. Now, from this peak to the line of reactant is your activation energy, EA. Activation energy, EA. And of course, this is your product, and this is your reactant. And between the line of product and the line of reactant, we have our delta H, which is enthalpy change. And this peak, like I said, is activation complex. Activation complex. So this is representing energy profile, an exothermic reaction on an energy profile diagram. Now, a catalyst do affect the rate of a reaction. if catalysts do affect the rate of the rate of a reaction. And how exactly does it affect the rate of a reaction? It does that by lowering the activation complex or activation energy. It does that by lowering the activation energy. That is what a catalyst does. So it lowers the activation energy from in a reaction. Now let's look at how this catalyst can affect the energy profile diagram for a given reaction. As you know that this is our line, we have the reactant line, we have the HR, we have the HPR, and reaction start from the and terminate at the line of product. So this is reactant, this is the product, and when you trace, now you see the catalyst, it will lower the activation complex. The activation complex that was high, you see it coming down to a lower level. So you see, this is the line without catalyst, the curve without catalyst, and this is the curve with the catalyst. And you have the activation energy of the catalyzed reaction. We also have activation energy for the uncatalyzed reaction. So this is a reaction pathway, reaction path. This is the effects of a catalyst on an exothermic reaction. The effect of catalyst on an exothermic reaction. Now let's look at the effect of the same catalyst on an endothermic reaction. How does a catalyst affect the energy profile diagram? Now let's see. Now we have the two marks. So for an endothermic reaction, the heat of product is higher than the heat of reactant. And the reaction commences from the heat of reactant and terminates at the heat of product. Now for the effect of catalyst, the catalyst brings down the activation complex. Now when you trace the line of product, and you trace the line of reactants, you will see the energy level that have been brought low, the EA that have been brought low. Now from this point, the peak to the heat of reactants. you have your EA of the uncatalyzed reaction. And from here, you have the EA of the catalyzed reaction. This is for the catalyzed reaction. EA 1. This is for the uncatalyzed reaction, and this one is for the catalyzed reaction. EA 2. This is our reactants, these are products, and of course you know that between this and this is our delta H, change in heat content. So I want to believe that with this explanation today, you are having some understanding, some level of understanding with the topic that we are considered today. I wish to let you know that this class will be continuous, and I want to admonish as you watch this video, please try and help me to subscribe to this video channel, and as you continue to get more from this channel, God bless you.